Okay, electrochemistry. In this unit, we're going to look at chemical reactions that involve the movement of electrons. Okay, we're going to review a couple terms because we've actually looked at these types of reactions back in Chapter 4. They are called oxidation-reduction reactions. Just to kind of refresh your memory a little bit, oxidation is losing electrons and reduction is gaining electrons. Okay, the reducing agent, that is the thing that is oxidized. That's the thing giving up the electrons. And the oxidizing agent, that's the thing that's being reduced. It's the thing that is accepting electrons. Half reactions. Okay, that's where we are going to split our reaction into two smaller reactions. One that just involves the oxidation and the other that just involves the reduction. If you need to, you may want to go back and review balancing with half reactions. We won't address that specifically in this discussion, but you are responsible for knowing how to do that for this unit. Okay, so let's take a look, all right, here's a redox reaction, and what we want to do is we want to look and see basically what's being oxidized and what's being reduced so that we can break that into half reactions. And so we're going to use our rules for assigning oxidation numbers, and again, those are back in Chapter 4 of your text. But here we have the hydrogen there is a +1, the oxygen's a -2, which makes the manganese a +7, +2 on the iron, +2, manganese +3, and then a -2 and a +1. So if we look at what's changing, the manganese is changing and it's becoming less positive, so it's being reduced. So we've got the MnO4 going to Mn2+ as our reduction, and then the oxidation is the iron 2+ going to the iron 3+. Okay, so if we pull together everything for the reduction to make it balanced, we get this as a half reaction, and then the oxidation, we get this as the half reaction. Okay, galvanic cell. This is basically a set of compartments where we have each half reaction occurring in a separate compartment, and then we connect the two compartments with a wire and force the electron to move from the oxidation cell into the reduction cell. Okay, so we're going to cause the electrons to be transferred externally so that we can actually do something with those electrons, with that energy transfer. Okay, so a couple of new terms. Anode. The two cells have electrodes in them, and the one at which oxidation occurs we call the anode, and we give it, or we assign it, a negative charge, and the cathode we assign a positive charge. That's where the reduction occurs. Okay, a couple of mnemonics to help you learn these. Oil rig, oxidation involves loss, reduction involves gain. And then Leo the lion says grr, lose electrons, oxidation, gain electrons, reduction. So there's a couple of ways to kind of keep the two processes straight. Okay, so here's a drawing of a galvanic cell. So we have our anode here, and we are losing electrons. Get my red pen back. Okay, so we're losing electrons here, and the reduction occurs at the cathode. We are gaining electrons there. Okay, the cathode contains the oxidizing agent. The anode contains the reducing agent. If this were if we needed to know a charge or to assign a charge, we would call the anode negative and the cathode positive. Okay, a couple of things to note. If you think about it, if we just had the two cells separately, all right, and we had, say, electron movement, okay, here, what we would see is we would tend to have a buildup of negative charge in this half cell and a positive charge in that half cell. And so in order to prevent the buildup of charge and to allow the electron flow and the redox reaction to proceed, we have to have some way to basically allow the balancing of the charge. And so there are a couple of ways we can do that. One is called a salt bridge. And a salt bridge, this is basically a glass tube, and it usually has some glass wool inside and then a very concentrated electrolyte solution in there. So we'll have within here, we'll have some positive ions, and then we'll also have some negative ions. An example, potassium chloride, that's a common component of salt bridges. And so basically what this will do then is as negative charge builds up here, the positive ions will migrate out to neutralize that charge buildup or to prevent the charge buildup. And again, here we'll have a negative charge migrating out there. Okay. Another way that you can allow the flow or to prevent the buildup of charge is through a porous disc that's between the two cells, and that way you can get ion flow as needed to prevent charge buildup within each of the half cells. Cell potential. Okay, cell potential is a measure of the driving force on the electrons when we connect two half cells together. This potential is based on the difference in affinity for electrons of the two half cells. In other words, one of the cells is going to have a stronger pull on the electrons than the other one does. And so the magnitude of that difference is a measure of the potential energy that is available from that combination of half cells. Now, to look at a particular setup, we first have to see what are the values for each of the half cells. And so these are available in a table in your textbook. Page 796 has a table of standard reduction potentials. These are measured at standard condition, so that's why we get these are E naughts. Standard conditions, the solutes are 1 molar concentration and gases are at 1 atmosphere. Now, we can't measure just the potential energy of a single half cell. We have to measure it against something. And so these values basically come from the setup that you see here. This electrode over here, this is called the standard hydrogen electrode. And all of the values that you see in your table came from measuring that half cell against a standard hydrogen electrode. And the standard hydrogen electrode is defined as having 0 volts of potential. Okay, so they defined this setup as 0 volts, and then they connected it to each of the others to see what the potential would be. And so let's see, for example, here we look at this setup here with a zinc cell, and we see that compared to the standard hydrogen electrode, the zinc has a lower affinity for the electrons, meaning that when we hook those two up together, the electrons flow out of the zinc compartment and into the hydrogen compartment. Okay, so that means that the zinc compartment is the anode, that this is being oxidized. So the reaction that's going on here is zinc is going to zinc ions, and we're losing 2 electrons, and those electrons are flowing through the wire. So the zinc oxidation against the hydrogen electrode produces a value of 0.76 volts. That's our digital voltmeter reading right there. Okay, that is the value for its oxidation. What you need to look at is the fact that in the standard reduction table, all of these are written as reductions. So when I flip this to write it as a reduction, all right, in other words, the way that you see it in the table is as a reduction, and you'll notice that the reduction potential for that is not a plus 0.76 but a minus 0.76 volts. Okay, so what this is saying is that relative to the hydrogen electrode, the zinc has a lower affinity for electrons, so the electrons are going to be lost from the zinc metal and be gained by the hydrogen. Okay, so let's look at another one. Here we have zinc and copper. Okay, both in the 2+. So if I look these up in the table, all right, say I wanted to figure out, maybe I don't know, I didn't have a voltmeter hooked up, and I didn't know what kind of potential I was going to get from these because I didn't know what's going to happen when I hook them up. So how can we tell from the table what's going to happen when we hook these up? Well, there's my zinc reduction. There's my copper reduction. All right, and if I look these up in the table, okay, the zinc reduction is at a minus 0.76 volts. These are our E0 values. And the copper 2+ to copper metal is at a positive 0.34 volts. Okay? Now, the more positive the reduction potential, then the more likely it is to be reduced. And so what we would predict then is when I hook these two half cells up is that the copper is going to be reduced and the zinc will be oxidized. Okay, and it's going to have a potential of the oxidation. You just flip the sign. All right, so these are the two reactions that are going to be occurring. And if we want to know what the potential is between these two half cells, we just add the two values. So my E cell, that's the potential when I hook up these two half cells. In this case, from the reduction, it's 0.34 volts. And from the oxidation, it's 0.76 volts, which would give me 1.10 volts. Okay. So we looked at that. So here we have our E cell, again, this is our E0 of our oxidation plus the E0 of our reduction. I guess I talked ahead of my slides a little bit. Okay, here's another example here. This one, we have the complete written reaction, and so we can look and see here that the iron is being reduced and that the copper is being oxidized. So if we look up our values in the table, okay, these are the two reductions, and so if we look at that, it makes sense. Then the iron is more positive than the copper is, so the iron will be reduced when it's hooked up with the copper cell, and so we're going to reverse, whoops, oh, go back. So we would reverse the copper, oops, copper yields. And so the E naught of that is going to be a negative 0.34 volts. Okay. The other thing I wanted to point out here is, remember when you're adding half reactions that you have to make the number of electrons equal? And so we would, if we were going to write the balanced, a balanced equation here to show what was happening, we would have to multiply the iron by 2, so that in the final balanced equation we would get the electrons to cancel out. The thing I want to point out in here is, when we do that to balance it, that does not change the potential of the cell. Okay, so multiplying through that equation to make the number of electrons equal, we still keep the standard potential the same as the one that came out of the table. All right, so here is our balanced equation, and the E cell for this then would be minus 0.34 plus 0.77 volts.